Okay, in this section we're going to be talking about Kepler's and Newton's laws. And then from that we'll talk about gravity. So here is Johannes Kepler. He was kind of an interesting character, like they all were back then. Didn't speak about this before, but apparently he and Tycho Brahe had some run-ins with each other. Brahe didn't want to provide the data to Kepler, and there are stories out there to indicate that Kepler poisoned Brahe. I don't think that's the case, but you can look that up and find out more about the personalities between these guys. It is an interesting story in and of itself. Kepler and Galileo were contemporaries of each other, and there are some interesting pictures about Kepler's 3 laws and what he was trying to do with them. This picture, I believe, indicates that he was trying to fit his 3 laws of planetary motion into something of the perfect Platonic solids. Turns out that is not something you can do, and in fact he was the person to figure that out. Kepler's first law is that all planets move in in ellipses, not circles, and the sun is at one of the focus, and the other focus there's nothing going on there. And here's the path of the orbit, and here's the planet that you got. You can take a look at a simulation of this thing at the NAAP website. The first law has indications that look like this. If you plot the orbits of the objects that are going around the sun, this is what you would see. The things that look like circles are really not circles. So here's the sun, here's Mercury, here's Venus, here's the Earth, here's Mars, there's Jupiter. If you look very carefully, even on this scale here, they're going to look like circles. But in reality, they are ellipses, and when you look at the data that's provided, then yeah, you can figure out that they are ellipses and that they sort of appear to be squashed circles. Kepler's second law, I realize, that this thing sort of doesn't mean much to folks, but the idea is this. If you are further away from the body that you're orbiting, so if you're further away from the sun in your orbit, you will move more slowly. So it takes a longer amount of time to go from 3 to 4, as opposed to from 1 to 2. Okay? You're going very quickly around here, and this is the area that people are talking about. This area compared to that area. And you could easily imagine that these two areas are the same. Basically, you have short and fat versus long and skinny. Okay. Now, Kepler's third law is one that allows us to calculate the distances between those planets and the sun. If you use solar masses, or if you use astronomical units to calculate the radius of the orbit and the orbital period in years, then r cubed over t squared is equal to 1. Okay, 1 astronomical unit, 1 times 1 times 1 is still 1. And then if you divide by 1 year, then it's 1 divided by 1 times 1. So you have 1 cubed divided by 1 squared, that's still 1. So it's not very useful for the Earth. Its usefulness comes in when we measure the period of, say, Mars or Jupiter or Mercury or Venus or the other planets, and we find out what their period is, and that allows us to figure out how far away they are from the sun. So that turns out to be quite useful. And if you put it in terms of distances from the sun and periods in terms of the Earth's orbital period, then what you're going to get is solar masses as your answer. You can apply the same equation to Jupiter, but in this case it's going to be in terms of, it's going to be a very, very small number, because Jupiter's mass is very small compared to the sun's mass. Okay, but the same equation applies. It applies for any body going around another one gravitationally. Okay, so the problem is this. Kepler's laws worked, but nobody understood why. And the question then comes up is, what's causing this attraction? And Newton has this issue too, as to, he called it a gravitational force, but what does that mean? And how does one body know that the other one is nearby? And that's a question that Einstein was worried about. So these questions really are not answered. The why question is almost never answered. We can always come up with hows, answers to the question how. But the question of why is sometimes thought of as to be impertinent or doesn't make sense, like why is white white rather than red? What is the color of jealousy? Or, things like that. Some questions don't make sense. And I don't know if these why questions make sense or not. All right, here's Isaac Newton. He is thought of very highly. Here are some important concepts as far as astronomy is concerned. And he was not a contemporary of Galileo. He came after Brahe, and basically it goes Brahe, and there was overlap with Kepler. Kepler and Galileo were contemporaries. They actually wrote letters to each other, and Isaac Newton came later. This is the Principia by Newton, and it's one of the books in the Great Book series. I've actually have a copy of this. It's very, very hard to read. Okay, now the next thing I want to show you is this video showing the 3 laws of Newton. And it looks like it doesn't want to let me open it up yet. But the 3 laws of Newton are, first of all, the law of inertia, which basically says that an object's motion doesn't change unless an outside force is exerted on it. And there are a couple of videos I want to show in regards to that. And then and this is an indication of it. So imagine that you're in a car and you're traveling around and your car has just been armored-alled. So the seat is very, very slippery and you stop very suddenly. Do you stay on the seat? No. You start sliding off. So that is one example of, there is no friction between you and the seat now, and so you go sliding off. Newton's second law is this one. Force is equal to mass times acceleration. And force is the idea that, something, you push something or you pull something. Acceleration is the change in velocity over time. So, like you are at a standing stop in your automobile and you press your foot on the floorboards, on the gas pedal down to the floorboard. You're going from a velocity of 0 to a velocity of 60 miles an hour in a short period of time. That is acceleration, the change in velocity over time. Now, velocity has a peculiar definition for us in physics, or in science in general. And that is, velocity is an indication not only of speed, but direction. As an idea to help with this idea, or an example for this idea, is consider I want to drive and get down to San Diego, and I'm going to drive at 60 miles an hour. Well, if you know San Diego is roughly 120 miles away, you would think it would take me 2 hours. What would you say if I told you that I drove at 60 miles an hour, but I really took 4 hours to do so? What would you think? Well, I think you would probably come up with the realization that I did not go straight there. That instead I took, I went about in a roundabout way, perhaps going to Temecula first, and then to El Centro, and then I got to San Diego. All at the same, all traveling at 60 miles an hour, but I did not go in a direct path to San Diego, but I took a roundabout one. That is the idea that I want to get across. Velocity has direction and magnitude. Okay, so if I change my direction while keeping my speed constant, then I am being accelerated. Okay, and here we can use the example of you being in a car again and traveling east on the 91 freeway and then going north on the 605. If your car is armor-alled, okay, and you are taking that interchange and going east and then going north, your body will slide out towards the outside edge of the car, unless you are holding the steering wheel such that you stay put in the seat, or your seatbelt holds you in. Basically, you would be, unless you have some friction between you and the seat, you would go flying off straight ahead. You would be continuing going east on the 91. The other thought to think in this case is you have to slow down and stop going eastwards. At the same time, you have to pick up speed and go north. So change in velocity is both change in speed and change in direction. All right, now there's a relationship between the force and the acceleration, and that has to do with the mass. Okay, so a more massive object requires more force to cause the same amount of acceleration. Okay, so in this case, think of a little Volkswagen Beetle or one of those smart cars in comparison to, say, a Humvee. And both are broken down on the side of the road. It's probably very easy for one individual to move the smart car to the side of the road because it's so light, and it would probably take quite a few people to move the Humvee over, supposing that all are pushing just as effectively as the other people, but it would take more force to move that heavier object than the lighter object. Okay, so that's the idea between force is equal to mass times acceleration. The other point I want to get across is in physics, and astronomy for that matter, we are interested in following how things move. And so what I'm really interested in this equation is the A. The A will describe how that particle moves given the forces that are acting upon it. So to talk about this again, when we have several forces acting upon an object, then the several forces add together in a vectorial sense. This means, suppose you are being dragged about by somebody by your hands, and then somebody else takes your hand and moves at a direction that's different than the first person. You're going to sort of go in between the two people as far as how you're being dragged about. In fact, if both people are of the same strength and they are pulling you from directly through a line between you, through you, then you might unless they start pulling your arms apart and pulling your arms from your body. Hopefully that doesn't happen. But in that particular case, you would be stationary. You wouldn't move at all because you have equal forces on both sides and they cancel each other out. Okay, so that being said, we're going to see, we're interested in the acceleration. Now there is a connection between mass and weight, and that connection has to do with the acceleration of gravity. Okay, so mass and weight are different. Mass is an intrinsic characteristic of some particle, something, and weight depends upon gravity, on the interaction between, say, your nature and the Earth, or your nature and the Moon, or Jupiter, or Mercury, or what have you. And here's description of it. The weight is equal to your mass in kilograms, the SI unit, and here is the acceleration of gravity. So for somebody that has a mass of 75 kilograms, their weight is 735 newtons. So, the implications here of this are what happens when m is small, when m is large, and what happens when force is small or large. Those are the things to think about in the second law. I have several movies to show you, but one of them is basically this. There is a force that's acting upon this ball, which is always directed inwards, okay? And that is through the tension of the string. Now, if you cut the string, then the ball doesn't have any more force on it anymore, and it will continue to go in the direction that it was going. The velocity doesn't change because the force is no longer there to cause it to change. And so the ball, the string breaks, there's no more force acting upon this ball, and so it's just going in the same direction, same speed as it was going before. Newton's third law is described here, and I really like it in terms of on this terminology here. When you push on something, it pushes back. Or even better yet, if you cannot touch unless you're being touched. I don't know, that seems kind of very interesting, very profound. You cannot touch something unless something touches you. Not only physically, maybe emotionally too. All right, so the question that I would like to ask you is now this one, and that is, let's go through here some examples. Consider this. You're traveling up US Freeway 99 on the way to Bakersfield and Fresno during the spring or fall. There are lots of grasshoppers on, flying around, eating up all the produce and things like that, and they hit your windshield, just splatter it, right? So the question is this. Newton's laws are basically saying that the force between the car and the grasshopper is equal. And what I want you to think about is, how do you go about showing that? Is it true? Is the force that the grasshopper, is the force of the grasshopper on acting upon the car the same as the force of the car acting upon the grasshopper? I mean, after all, the grasshopper gets squished. The car doesn't get squished. So how can it be true? So that's something to think about in the discussion topics. Okay, so here is the first video I wanted to show you. It's kind of a fun one, and it will basically give you an interesting feel about Newton's laws. Maybe this is just my maleness coming out, but I think this is a fun video.
Every object stays at rest unless acted upon by an outside force.
Notice both objects change their velocity. The seated person moves, and the person that was flying slowed down.
Newton's third law. For every action, there's an equal but opposite reaction. Whenever Whenever one object exerts a force on a second object, the second object exerts an equal and opposite force on the first.
This is a production of the United States and Oswego Technology.
Playing chicken with the train, playing chicken with the train, train. Oh no no, oh no no, you know that I'm playing chicken with the train, playing chicken. Every object continues in a state of rest or of uniform motion in a straight line unless it is compelled to change that state. I can't read this. I can't see it. Yes. Every object continues in a state of rest or uniform motion in a straight line unless it's compelled to change that state by the forces impressed upon it. What is that state stand for?
I'm almost... Okay, I'm not going to hit you, Mikey, but just saying, I'm going to run by you.
Alright. Every object... I cannot do this. My brain is not functioning. It's mush right now. Every object stays at rest unless acted upon by an outside force.
Holy shit! I hit your head that time!
You hit my head every time.
Well,
That
that's...
was by an outside force.
I hit your head that time!
It is inversely proportional to the mass of the object. Action. There's equal but opposite reaction.
The second video I want to show you is this one. It's basically a very old video, but as they say, oldies but goodies. And this one is, you can see that the motion is independent of, well, one motion is independent of the other, and it behaves in a vectorial sense, namely the motion in the x direction or horizontal direction, as we'll see here, is independent of what's going on in the vertical direction. What you'll be seeing is an airplane flying across the screen, and a flare will be thrown out. This flare is initially going at the same velocity that the airplane is, after all, but later it will change a little bit as nothing is holding it up in the air at the same elevation as the airplane, so it will fall. Gravity will grab a hold of it. But at the same time, the initial velocity that the flare had, namely traveling with the airplane, will still be evident. The flare barely slows down as it goes across the screen. It's going about 100 miles an hour from left to right in the beginning, and it will continue being maybe 95 miles an hour when it gets to the right side of the screen. On the other hand, the vertical motion, you'll see, is quite stunning. It just hangs there in the beginning, and then by the time it gets close to the water, it is really moving.
Is the flare always under the airplane? Does the flare fall directly below the airplane? Describe the motion of the flare with respect to the airplane. With respect to the Earth, what are the forces acting on the flare? Which component of the projectile motion are you seeing with this head-on view? Give evidence to support your answer. Describe the motion of the falling flare as seen from the airplane.
Okay, we'll cut it off there. Thank you.